Even if we could quantify the correlation between the 30 plus first-tier parameters and the hundreds of second-tier parameters we discussed last time with respect to the coking result, this work is far from enough to accurately predict the outcome of the coke produced. Because the causal relationship between many of these parameters is a complex, non-linear relationship. To apply this to the prediction of coking results, complex mathematical simulations are needed to establish a big data model for coke prediction. Therefore, 10 years ago, we brought in a big data expert, a graduate of Peking University's mathematics department, to serve as our general manager. 4 years ago, this project won the first prize for scientific and technological progress in Shaanxi and has been successfully applied in the industry. Today, I will first introduce the principles and logic of how to establish and apply the big data prediction model for coke. This diagram illustrates coal's first-tier parameters. We define this block here as basic value parameters, which are the parameters we are mostly using today. The second part consists of parameters in other components that have a positively correlated influence on the coke result. We define the third part as the negatively correlated parameters. The objective of studying this data is to determine how to produce coke with a lower cost while satisfying the product quality requirements. This is the fundamental goal of our research. The main work the system needs to accomplish is how to find the coal with the best cost effectiveness and the lowest cost coal blending solution. Therefore, we must match the real-time price of every raw coal material with all of that coal's parameters at all times. This allows every parameter of every coal to form the cost effectiveness of the parameter. In other words, we transform each single coal into 30 plus independent parameters and turn several coals in the database into several sets of 30 parameters for matching. This allows us to find the best solution at the lowest cost, realizing the maximum value of the big data model. The logic here is that for every coal at a different price, those 30 parameters become 30 independent parameters with assigned weightings. Every single parameter, especially those with nonlinear relationships, requires an independent data model. For example, taking calcium as a single parameter. If two coals have different prices, the weighting of the same amount of calcium is different. If the coal blend requires calcium, the big data model will find the calcium with the lowest cost based on this weighting. This then increases the weighting of the coal that provides the lowest cost calcium. Once we quantify all parameters for all coals, the system will find the coal with the highest cost effectiveness and the optimal cost blending solution for different products.